Hmm. This last part here is the most complicated situation. I have 15 minutes, 14 minutes. I'm going to see how far I can get with this. We might be able to only work through part A of our example, but let's try. So sometimes we need to set up a definite integral to model the amount of work done. A classic example is lifting a rope hanging vertically from the top of a building. So I have the question, why is this a variable force situation? So I feel the need to draw a picture over here, but my space is horizontal. I have a vertical building, and I'm wondering if it's confusing if I try to reorient it horizontally. So maybe I'll draw it off to the side over here. So here's our building. And then here's our rope. Our rope is hanging over the side of the building like this. And I claim that this is a variable force situation. So why is this a variable force situation? Well, the thing is, when we want to pull this rope up, it takes very little work to pull the top of the rope up, the very top of the rope up. Why? Because the top of the rope just has a little bit to go. You know what I mean? Like, on the other hand, the bottom of this rope has a lot of work to do. Why does the bottom of the rope have a lot of work to do? Because we have to pull this little piece of rope down here a much greater distance than we do the top of the rope. So I would say that this is a variable force situation because the pieces of rope at the top of the building travel a greater distance than the piece near the bottom. Does that make sense? So, so here's what's going to happen. I am going to imagine that my rope is here like this. Okay. I am going to chop this rope up into n pieces. So chop up rope into n pieces. I'm going to calculate the amount of work done in moving each piece to the top of the building. And then I'm going to add up all those works. Does that make sense? So I'm going to call the top of the building distance 0. The bottom of the building, the bottom of the rope is distance 100, like this. So I have n pieces of rope, right? So if I were to look at just some generic piece of rope over here, and I were to calculate how much work is done in moving that piece up. Well, one way you could think about it is you could think of, when we chop it up, this is like x0, this is like x1, x2, blah, blah, blah. This is like xi minus 1, and this is like xi. So right now you should automatically be thinking we're in a Riemann sum type situation like before. Okay. And I want to talk about moving this ith piece of rope. So how do I figure out what that is going to be? I'm going to call Wi the work done in moving the ith piece of rope. Oh my God, Jason, did I forget to post these notes? I thought I posted it in the announcements.
I have no. Oh, it's an announcement.
Yeah,
Oh, sounds good. My bad.
no, I may have not posted in the announcements. Take a look, hold on. It's a little late now, so if I didn't, I'll just post it after class. Yeah, it's in the announcements. So, and I'll post these notes to class as well. So we know that the work, sorry. We know that the work is equal to the force times the distance, right? I'm going to say that the distance, what's the force going to be? Well, the force kind of depends on the weight of the rope, right? So if you think about how wide this piece is, this piece from here to here, this amount of rope is what I'm called delta x. And delta x is going to be equal to b minus a over n. In this particular case, it's 100 minus 0 over n. So the length of that little piece of rope is 100 over n. So I'm going to take that length times the weight per unit of length. That's going to be the force. So let me write that down. So this will be, the length is 100 over n. And the weight per unit length, the weight per unit length is just going to be 200. It's because it's a 200 pound cable, but the total length is 100. So it's going to be 200 pounds per 100 feet, right? And the length was in feet. So I hope you can see that when you look at those units cancel. The 100 over n feet cancels with the feet there. And then we end up with this number, which is the amount of pounds we have. Okay. And then what I wanted to do was I wanted to figure out how far I had to move this. So we're going to call the distance that we have to move this from here to here. We're going to call that number xi star. Okay. So our distance is going to be xi star. Xi star. So let me clean this up a little bit. What we're going to have is we're going to have 2, because 100 divided by 100 is 2. I'm going to have my xi star, and then I'm going to have that multiplied by 100 over n, which, I want you to remember that this guy is my delta x. Okay. So in the end, we're going to get wi is equal to 2 times xi star times delta x. Now, oh shoot, I'm gonna run out of time. I'm just gonna wrap this up real quick, sorry. So the amount of work is approximately equal to the amount of work done in each of those n pieces, which in this case is going to be the summation is I goes from 1 to n, 2 times xi star times delta x. I know that the actual amount of work done is going to be the limit as I let the number of pieces go to infinity. So it's going to be the summation as I goes from 1 to n, 2 xi star times delta x. I hope you recognize that we can express that as an integral. It's going to be 2x dx like this. And we're moving it from, we're letting the x values range from 0 to 100. This goes from 0 to 100. All right. So I just find the antiderivative, that's going to be x squared. I evaluate that from 0 to 100. Whoops. Yeah. 0 to 100. And then I'm going to get 100 squared minus 0 squared, which is 1 0 0 0 0 10,000 foot-pounds. Not divide, foot-pounds of work. So I think this was a little bit rushed at the end. I hope I didn't mess it up, but hopefully you get the basic idea.